Hello! So it's April, and that means Easter is only just around the corner, which means it's time to make another Easter game featuring bunnies and Easter eggs. This time, I thought I'd make something a little different, more of a proof of concept. You see, I saw this video about making a horror game that's impossible to screenshot. It uses two layers of static random noise, one moving and one standing still. But because of the way this works, if you try and take a photo or pause it, the game just disappears. So I thought, could I make an AMIGA game that uses this technique? Well, not being able to take a photo of the game, or pause it for that matter, is an interesting trick, but it's not the only trick I'm planning. What I want to create is a simple Pac-Man-like game, except the maze will disappear if the player stops moving. And the thing is, how can we create all of that in Amos? Well, in this video, we'll find out. Firstly, we'll need to do a few experiments to determine what looks best and what's the most efficient. Feel free to skip ahead if you just want to see the final game, although here's a quick preview of me playing it. Now, I'm going to be working with Amos Professional, so let's take a look at my first experiment with this technique. First, I started with this procedure called Prep Static. I opened up a screen, number 7, and filled a 16 by 16 area with random pixels, and I repeated this 16 times. After each one, using Amos's get block command to save a copy. Filling an entire screen with the plot command alone would be far too slow, so instead, I'll fill the top left hand corner of the screen with the 16 blocks I've just made randomly. Then I copy the left hand side of that screen to the right hand side, and then finally the entire top to the bottom, which gives me a full screen of random noise. Next, I create this procedure to draw the level randomly. It starts by reading the state of the joystick and incrementing or decrementing the values of XX or YY, depending on which direction the joystick is pushed. You might have noticed that the add command has 2 extra parameters on the end. This is a special feature where Amos will count up to those limits and then wrap back around again for you. After this, I start to draw a potential level based on the big data block at the bottom, with a 1 representing the foreground and a 0 being the background. If a 1 is discovered, we paste a random block down at that position. Remember that each position in that represents a 16 pixel square. If a 0 is discovered, we copy a section from that full screen of noise we created in the previous step, offsetting it relative to how the joystick had been moved. Finally, this tiny block of code calls our function to make the noisy background, create a new screen, and then sit in a loop rendering the level. So let's take a look at that running. And we can see the random noise, and as I move the joystick around you can see it move around as well. But this isn't exactly a good effect, and besides, that code is redrawing the entire screen every frame, not leaving much time to do anything else. I don't think the animating random noise idea is really the answer, so let's try something better. Starting again with my prep static function, but this time it's only generating 16 sets of 16 by 16 tiles. Then we have our level draw procedure, same as before, but this time we only paste one if one of those tiles is an empty space. Now, setting up the screen is a little bit more complex. To prevent having to redraw things, I'm going to use the dual playfield effect. This allows you to create 2 different screens and have colour 0 of the first one be transparent so that you can see the second one behind it. The background one, screen 0, I'll make twice the size and fill the 320 by 200 parts with random noise tiles, much like the first program, filling a quarter of the image. I then use screen copy to copy it to the other 3/4 of the screen. I then trigger the dual playfield effect and cross my fingers. Dual playfield in Amos can be a bit buggy sometimes. Finally, I call those 3 procedures to set up the display. Now this strange line here that sets up a screen offset of 1 across bypasses one of those dual playfield bugs that prevents smooth horizontal scrolling. Then I set up a palette and after a key press, change it to a black and white one. In the main loop, we have the same joystick controls as before, but this time we're going to use the screen offset to move which part of the background we see. The advantage to this method is all of the movement is done in hardware, leaving us all of the CPU time. So let's take a look at this. Firstly, with this weird colour palette you can see the game map and the background quite clearly. Now watch what happens when I press a key. It's all disappeared! Nope, it's not broken. Here's the really neat bit. I'm going to move the background around with the joystick, and just like that, whilst the background is moving you can actually see the level. Now here's the sneaky bit. You can't pause it or take a photo. Go on, try it. Pause the video and the game map will completely disappear. Crazy, isn't it? That's a really cool effect. Right, well that's a perfect proof of concept. We've managed to create a suitable effect that disappears when you stop moving, and the entire trick is being rendered using the Amiga's hardware without us drawing anything to the screen at all. With that out of the way, we can start to get on with the game. Now, I'm sure all of you know how to play Pac-Man, and that's kind of where I'm going with this game, although there'll be a few small differences. Firstly, we'll be collecting eggs rather than dots and power pills. Instead of the pizza-shaved protagonist, we're going to have a cute bunny. Thirdly, instead of ghosts, we're going to have, spiders, because, well, why not? For bonuses, we'll have just one, a carrot, because there's that theory that eating carrots gives you better eyesight, so when the rabbit eats one, we'll change the palette temporarily so you can see the game map again. First up, we need to do some graphics, so let's get drawing. But before we look at that, I just want to give a quick shout out to all my Patreons, and I thank them for their support. And if you'd like to join them in supporting me, then follow the links in the video description. For all of the objects on screen, I'm planning on using the hardware sprites, and this instantly gives us some limitations, and not to mention, Amos can get a bit funny with sprites and dual playfield enabled anyway. Let's see how we get on, starting with our rabbit. And if you remember back to last year's game, the rabbit always faced away from the player, and I think this image would also work perfectly fine for our top view as well. But they're bigger than the 16x16 sprite size we need, so I've shrunken them down, and I've created 4 sets of them, one for each direction of movement. Perfect! These sprites are 4 colours, one being transparent. We also need some spiders, and here they are, 4 frames for each direction, and each one being 16x16 in size. If you obtain the power pill in Pac-Man, or in this case, the large Easter egg, then just like Pac-Man, they'll run away and be vulnerable, so these images will do for that. Whilst they may be only 4 colours, depending on what sprite number we use, we can assign different palettes to them. Finally, if you capture one while they're vulnerable, well, I guess splat one, then we need a different image. Okay, it's not that much different, but I intend them to stop moving for about 10 seconds when this happens anyway. Now, these 2 egg shapes will be what we need to collect. Currently, they're all one colour, but we need to make random noisy versions of these inside the game for them to disappear when there's no movement. These won't be sprites, they'll be drawn onto the foreground. Finally, we have our bonus carrot. Now ideally, I'd like to have 4 spiders and 1 rabbit, that's 5 sprites. That leaves us 3, which means theoretically I can have a 16 colour sprite for the carrot. And sadly, things don't always go to plan. As an experiment, I set up the sprites, written up how they are in this box that's just appeared. Sprite 0 is occupied by the mouse currently, although it's easy enough to remove. Sprite 1 will be the rabbit, 2 to 5 are the spiders, and 6 is the carrot. Being a 16 colour sprite, it actually makes use of Sprite 6 and 7. But when I try to run this, well, watch what happens. There's only 3 spiders and no carrot. I can move the background around just fine, but there's no extra sprites. But when I break the program, the sprites are able to appear in the areas where the program interrupted window is. And it's even weirder when I drag this up and down. Now remember that strange screen offset command I had with the offset horizontally and vertically set to 1? Watch what happens when I reset that. Now we get 4 spiders and a carrot, although the carrot seems to have lost its colour. I don't think it's using Sprite 7 properly. If I hide the mouse and swap the rabbit and the carrot around, then we should have the best of everything. However, with that screen offset set, watch what happens when I scroll the game around now. See how the vertical direction is smooth but the horizontal now jumps in blocks of 16 pixels? Just to prove this, I've changed the code so I can toggle that screen offset and watch what happens. We can either have all the sprites we want, or smooth scrolling. I spent quite a while trying different combinations, even using the computed sprites, and the best I could do was get 3 spiders, 1 rabbit, and 1 4-colour carrot image displayed at the same time. Nothing I can do about that, this is what we're working with. These are long-standing old Amos bugs, and I think the more recent community versions may have fixed this. But anyway, let's stick with what we've got and get on with the gameplay. So first up, some bootstrapping. And to make things easier for now, I've defined some empty procedures that will populate later on. This means we can get on with the game and be in the habit of calling these procedures, rather than trying to find the places in the code later on to put the relevant functions in. These will handle the score, lives, level display, and sound effects. I've also stolen this procedure from one of my previous games. It wraps handling the joystick input and also provides keyboard alternatives at the same time. I've also created this procedure, which, given a position in a level, will return a bit mask of directions that we're allowed to move. Now, onto our prepare static procedure that you saw before, and the beginning hasn't really changed much, it still creates those 16 tiles of the random 16x16 pixel blocks. However, this part is different. This pastes image 60 onto the screen and then recolours the non-black parts to be a random colour between 4 and 7. I guess I could have saved it like this originally. The 4 random colours is only so later on I can choose 2 sets of them to be white whilst the other 2 are black, randomly, creating static noise without having to redraw them, as I can just change the colour palette. This is also repeated for the smaller egg too, except this time we're actually going to make 4 different copies to create a bit of variance. The weird colours you can see here are just so you can see what's happening. Onto the level, and I've defined this, and I know it looks complex, but each of the numbers represents a 16 by 16 square, and each number has a specific meaning, and I've colour coded things to help. This leads us to actually drawing the level, which starts by resetting some global variables. We need to be able to keep track of how many eggs are left, and also the initial positions of each spider, so we'll reset all of that first. Then we'll read each number from our map data, and if it's greater than 0, we'll stamp one of our random noise tiles down. If we find the number 2, we'll make a note of that position, as this is where the player's going to start. For 3 and 4, we paste our special egg images on the screen and increase our counter of eggs found. For 5, we record the positions for up to 3 spiders. We then convert this square back to a standard egg type square. Finally, if it's a 6, then we store where the bonus image sprite will be appearing. Running that gives us this image, and I've set the background and foreground colours in what I'm calling carrot vision. Later on, you're going to be able to collect a carrot, and this is the colour scheme I want to show. The dark cyan in the background is actually the background screen. So next up, let's get that player sprite moving around. The player movement starts with remembering what the previous movement state was, and then grabbing an update from the joystick. The joystick information is a bit mask where bit 0 represents the up direction, 1 the down direction, 2 to the left and 3 to the right. So if all 4 bits are 0, then the joystick isn't being pushed in any direction. And when that happens, we restore the direction to what was previously being used. Now we only need to look at which directions we can move in when we're exactly on a square. And when we reach that, we fetch the allowed movement. If you remember from the previous section, the can go procedure also produces a bitmap that exactly matches the format of the data we get from the joystick, setting bits in the directions we can move. Which means to simply block directions we can't move in is as simple as ANDing the 2 values together. And if that actually leaves us unable to move, then we just restore to the previous direction we were moving in again. If that leaves us moving in 2 directions, i.e. a horizontal and vertical, then we need to select one of them. If we're moving horizontally, then we switch to vertical and vice versa. This allows the player to change direction by holding the joystick in a diagonal. Finally, if we're not exactly on one of the squares, then we need to continue to move, but only allow movement along the same axis that we were previously moving along. We then convert that final movement into a horizontal and vertical movement. This variable, last direction, which could have been named better, is the first frame index of the animation for the direction that the player is facing in. This just leaves us the task of moving the player and moving the background. So let's take a look at that in action. And as you can see, moving around is effortless and simple. I'm regularly holding the joystick in a diagonal too to make movement easier. Next up, let's eat some eggs. And all I'm going to do is insert a small block of code here. This code looks at the map square we're currently on, and if it contains an egg, then it will trigger a sound, increase the score, reset that map position to be just floor, paste a random noise bit over the top of it, and then decrease the counter of the number of eggs left to eat. Note the to do comment at the bottom for the larger eggs. Running that looks like this. That sure was easy to implement. Next up, we need to add the spiders and give them a little bit of intelligence. Not too much, just a little. So let's have a look how we do that. First up, I've created a bunch of arrays and made them global. Spider start X and spider start Y, well, we already had those. They're the starting positions read from the map data and are in screen coordinates. Spider X and spider Y will hold the current positions of each spider. Spider state will allow us to store the current direction or some other special states. And spider run and spider run time will be used when the player eats a big egg so we can make the spiders run away, but only for a limited amount of time. I also added 2 global variables which will hold how long spiders will run away for, and how long they will stay dead. Next, before the main loop, we'll need to initialize these arrays. Spider run equals 0 means they're all in chase mode, and spider state 11 I've defined to mean pause for a short amount of time before moving. And currently the amount of time it waits is based on the spider runtime value. To keep things tidy, the main loop will call a special monsters procedure, and that will handle moving all the spiders. The parameter passed is just a frame counter to keep the animations running nice and smoothly. This procedure iterates through each spider, and due to the issues we had earlier, it's using sprites 1, 3 and 4. If spider state is greater than 3, i.e. a special command, then we'll call another procedure called run spider, which is the actual brains, and after that, we'll update the frame number and display the sprite. If it's 3 or less, that means the spider is moving in one of the 4 directions. This code here, looking at spider run, changes the images from the spider from the normal one to the patterned one. If the spider run value is 2, that means it's dead or splatted. This code changes the frame again to the splatted image and watches the time. If it gets too close to finishing, it starts flashing the image back to the original. This is also the same pattern used if spider run is 1, only this time the runaway image is used instead. Note that this one only calls the run spider procedure every other frame, so they only move at half speed. Finally, in normal mode we just call the run spider routine normally. So let's have a look at the run spider procedure. And this starts out with that code that we need to delay them moving at the start. Once complete, the code then picks a random direction. A random direction is also chosen if the state value is set to 10. If it's not any of those, it's going to be 0, 1, 2 or 3, indicating up, down, left or right, and a horizontal and vertical direction is set accordingly. Just like with the player, we'll look to see if the spider has landed on an exact square, and if it has, we'll extract its map coordinates as well as the player's map coordinates. We only need to change the direction of the spider when it's exactly on a square. Firstly, if the spider is not in chase mode and with a bit of randomness thrown in, we scan the map from the spider's position in a horizontal and vertical direction looking for the player. Each of those scans will stop if it encounters a part of the map that we can't actually travel along. Once all the scanning is complete, one of 2 things will have happened. The value of L will be true and either the DX or DY will have been set along with the direction. Yeah, L could have been named a little bit better. If the player wasn't spotted, L will remain false, which leads to stage 2. Now there's 2 versions of stage 2, one for horizontal movement and one for vertical. They're more or less identical, so I'm just going to show you one of them. First, it checks which directions the spider is actually allowed to move and stores that in the variable p. I know, another bad variable name. If the spider was moving horizontally, we check if it's possible to move up or down, again with a bit of randomness. If the spider is already level with the player, then a random direction is chosen. Else, a direction is chosen that would make the spider move towards the player. And if we can't go in that direction, we invert it. Once successful, we set the states appropriately. Finally, if we still can't move, we'll keep trying to go in the direction we're currently going, and if we still can't do that, we'll change the state value to 10, which means next loop, pick a random direction. These DX and DY values are then just added to the position of the spider. Remember, there's one block of code just like this for the other axis as well. So let's see them spiders moving around. And after a small delay, they start moving, and each one travels in a different direction. That's what randomness is all about. They do take their time, but eventually, one by one, they do find the player and move towards it. At this point, I do think the player would be dead, so let's add some collision logic. Firstly, if you remember before, we left this to do here. Well, this code now changes to look like this, where each spider has their state set to 1, and we also invert the direction they're currently moving in. But we also need to be fair to the spiders too, so this line here uses the hardware to see if Sprite 0, the player, has collided with Sprite 1 to 4. Now Sprite 2 will be the carrot, so we'll ignore that, but for the others, we check each one and set the variable S to the spider we've actually collided with. The thing is about hardware collision is it's very accurate, and for the ones we're doing it's very unforgiving, as these two here would still be classed as colliding, but I don't want that. So this little bit of code checks if the player and the spider are within 6 pixels of each other on one axis, and on the other axis are in exactly the same position. And if so, then if the spider is running away, we make a splat sound, give us some points and configure that it's been splatted. If the spider is in normal mode, then we fade the palette to shades of red, decrease our lives counter, play a suitable sound and exit the main loop. So let's give that a try. Firstly, I'll go for the big egg. And then for one of the spiders. Oh, and another. Finally, I'll let the white one get me. Perfect. That's the basics done. Next, I want to get the bonus working, which will introduce changing the colour palette so when you stop moving, the game board disappears. So let's get on with it. At the start of the game, we ensure Sprite 2 is turned off. Sprite 2 will be the carrot, and we're going to simulate that carrot has been eaten. Bonus time is set to the time when the bonus carrot should next be shown, and carrot time is the time when the effects of the carrot should wear off. Finally, we set our nice pleasing orange palette. In the main loop, we add this short block which watches the clock, and when the time is finally reached, it fades the colours to black and white. When a player is exactly on a square, we also test to see if it's where the carrot is too, and if it is, we eat it, and then fade the palette back to the carrot colours. We also have this piece of code which, if the carrot is visible, removes it if it's been there for too long, with a short flicker before it goes. Finally, this block, which is quite important. If the player is moving, this controls the colours used to draw the eggs, randomly picking patterns of black and white. However, if our carrot vision is active, then it fixes them to a specific colour. And with all that done, we have the starts of a great game. It's very weird when the carrot vision thing fades in and out, and how you become accustomed to the map in either form, and it works really well. Once again, if you pause the video or stop moving the rabbit, everything disappears. So that leaves some game finishing touches, like adding the heads up display at the top of the screen, showing the current score, the number of lives and the current level you're on. That's easy enough to do, so I'm going to let you wait and read the source code for that. I also need to add some sound effects, and once again I've also covered that in a previous video, so I'm not going to cover that here. I'm also going to change the colour palette too, depending on the level, and actually create about 5 different levels too. The game also needs some music to make it really compelling to play, and what you're listening to right now is the music I'm planning on using, kindly shared to me by Virgill, and as always I'm very grateful for this. At the time of writing this, the demo party revision is only a few weeks away, and I've no doubt that Virgill is very busy, so I'm especially grateful for that. Now the other thing I want to create is a title screen, but I want it to glitch a little, so let's take a first look at what I made, and then I'll show you how I made it glitch. See how we start off with a rabbit, then it switches to that noisy background and you can just make out the shape of a rabbit. That's not a pre-made set of images, they're being generated in real time, so let's have a look how. The title procedure starts by unpacking our title image and then taking a copy of the rabbit image. Then there's this set of crazy for loops, which sample a smaller monochrome 32-bit sized copy of the rabbit into 2 arrays. The array rabbit rows contains bits set to randomly 0 or 1 where the rabbit image is, and the mask rows array contains bits set to 1 where the rabbit isn't. To render the static, I open up another screen that's only in 2 colours, and I find the start of memory for its only bit plane. I also store the number of bytes required between each row, or the stride. In the main loop there's 2 modes. The second mode, shown at the bottom, just draws the rabbit to the screen. Nothing really exciting there. But the first mode, now that is interesting. First it clears the area to black, and then it works through each row of the array we've previously populated. It generates a random number. Now Amos can't generate random numbers quite large enough, so I have to manipulate this a little. Then it computes what the bits on that row should look like by ANDing the random data with the mask rows array, which keeps the bits where the rabbit isn't. It then ORs this with the rabbit rows array, which puts the static rabbit image in place. I then use the load command to directly write this 32-bit number into RAM. Finally, this special command from the AMCAF library, bzoom, draws it to the main screen scaled 4 times the size in both directions. It's a much faster command than the Amos zoom command, and also, because the source is only in 2 colours, it only copies 1 bit plane. And that's it. I'll show you it again, but this time I won't hide the other screen so you can see what's happening. Very simple and very effective. There's no way you could draw it that fast using the normal graphics commands. So that only leaves one last thing, and that's for you to see the final finished game, with sound effects and music and everything. So, let's see how well I can play. I kind of think that turned out really great, considering it was actually just meant as a proof of concept, and it's clear it could be developed a lot further, but I think it holds its own quite nicely. The full source code for this game is included in the links in the video description, along with the actual binary as well, so you can play it if you want to right now. Anyway, I hope you enjoyed this video, thanks for watching, and I'll see you in the next one.